This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Well, let's start. Yes. Oh, good afternoon, good evening, everybody, and well done on braving what was 30-something, high 30s, and low 30s and 100% humidity and everything in between. Now we're in 19 degrees. One day, mechanical engineers will sort out how to keep a room at the right temperature. Well, at least it's better to be cold than hot. Welcome, thanks for coming along. We're very fortunate tonight to have a visitor to the university from the University of Wollongong. See if I can do this in a flawless German accent. Professor Gerhard Swiegers, or as an Aussie, we've been here for 30 plus years, Jerry Swiegers. But Jerry's talking to us about some research that he's been doing at Wollongong, but also very impactful research on green hydrogen production that's being commercialised as well through the company Masata, which he's founded, which is quite a remarkable piece of research and wonderful undertaking in general. So Jerry is originally South African, then did his graduate study in the US, then was convinced to come to the Australian National University for a postdoc in the early 90s for 2 years, and 33 years later he's still in Australia. Went to Wollongong after ANU, and CSIRO for a period, and was brought back to Wollongong to keep working on green hydrogen. And Jerry's with us today, the Professor at Wollongong. Jerry, a year and a bit ago, won one of the inaugural ARC, Australian Research Council's Industry Laureate Fellowships, which makes him, I wouldn't say a lucky dog, because I'm sure the proposal was as wonderful as the research I know does. He is so a deserving dog as well for a wonderful fellowship, which is giving him the opportunity to continue his research and really grow it in the collaboration with Masata. So tonight, Jerry is talking about some of his research in advanced electrolysis. So please welcome Jerry to the University. Thank you.
Thanks very much, everyone. Yes, so I will be talking today about a new type of water electrolysis that we developed called bubble-free capillary electrolysis and its application to industrial water electrolysis. So, first of all, let me start off just by talking about renewable hydrogen, which is also called green hydrogen. So green hydrogen is hydrogen that is produced from water using a device, an electrochemical device called an electrolyzer. And that electrolyzer, to make green hydrogen, has to be powered by renewable electricity. Now, green hydrogen is effectively a renewable fuel. In other words, you capture the renewable energy in a fuel, and it's actually a very energy-dense fuel. It contains 33.3 to 39.4 kilowatt hours of usable energy per kilogram. That is significantly more than petrol or diesel, which is around 12 to 14 kilowatt hours per kilogram, and way more than batteries, specifically lithium-ion batteries, which are only around 0.265 kilowatt hours per kilogram. So it's potentially a store of renewable energy that you can transport and use in other places. At the moment, green hydrogen offers the only viable way to decarbonize a whole host of economic sectors called the hard-to-abate sectors. These are things like shipping, aviation, heavy transport, and chemicals. And so if you think about a passenger aircraft flying between continents, there's no way that can be powered by batteries. Batteries just are not energy dense enough, but they can potentially be powered by hydrogen. And so that's really where hydrogen comes in. Those sectors at the moment produce about 30% of global CO2 emissions. And green hydrogen is pretty much the only way to decarbonise them. So there's been an enormous amount of work on green hydrogen by many think tanks and various nations. And it's generally agreed that in 2050, by 2050, green hydrogen is going to be around 20% of the world's energy supply. So if you think of the biggest industry on the planet is energy, and potentially it's going to be 20% of that industry. That means that we will need around 500 to 800 million tonnes of green hydrogen produced annually by 2050, which obviously translates to a vast decline in CO2 emissions, but for the purpose of this talk, it also translates to a huge demand for electrolyzers, around 5,000 to 8,000 gigawatts. And to give you an idea of that scale, the entire Australian electrical grid is less than about 50 gigawatts at the moment. So we're talking a huge demand for electrolyzers. So what are electrolyzers? Well, as I said, they are electrochemical devices that produce hydrogen from water using electricity. Electrolyzers have actually been around for over 200 years. The first electrolyzer was developed in around 1800, and they've been used industrially for well over 100 years. You know, back in the 1900s, the various governments were using them to fill hydrogen balloons, military observation balloons. Those were probably the first real industrial application for electrolyzers. So what do they consist of? So this is a picture of an electrolyzer, and you can see that there are two components here. Firstly, there's what's called a cell stack. So that's the thing in the front, that round thing. That contains many electrochemical cells all stacked in what's called a filter press arrangement. So each cell is disposed as a planar disc, and then you have many of these planar discs all stacked together, and each of those discs is producing hydrogen, and the hydrogen is all collected together, and it comes out of this thing called the cell stack. And then the second thing that you have, and they come in different sizes. This is a small cell stack that you can buy. You also get very large ones. In fact, some of the largest are probably, several meters high. And then the second part of it is what's called a balancer plant, which is the engineering system around the cell stack that manages the cell stack. So that's the thing at the back of this picture. And you can see there are various tanks and pipes and pumps and sensors, etc. there that manage it. The balancer plants typically are all automated. So they have a thing called a PLC, which will control what goes on inside the cell stack. It'll manage the cell stack. It'll manage the gases coming out, the pressure of the gases coming out, also manages the safety of the system. So the total energy consumption of an electrolyzer is the energy consumed by the cells, and that is by far the majority of the energy needed to make green hydrogen, and then also the energy consumed by the balancer plant. So why is energy consumption important? Well, the main reason energy consumption is important is because 80 to 90% of the cost of making green hydrogen is the cost of the renewable electricity used. It's what they call OPEX, or the operating expenditure. And so the more efficiently you can use the renewable energy, electrical energy coming in, the cheaper your green hydrogen is. The less efficiently you use it, the more expensive it is. And then the other 10 to 20% is the cost of the equipment, which is called the CapEx, or capital expenditure. Okay, so a few years ago, so I've been working in hydrogen probably for 30 years, but in the last, I'd say around 15 years or so, I've been working 12 to 15 years, I've been working in the electrolysis industry, in the electrolyzer industry. And a few years ago, I had some students, and we were looking at what is the next big thing going to be in hydrogen. And so we looked at how the architecture of electrolysis cells had evolved over time. And so this is just showing schematics of what electrolysis cells look like and how they've changed. So on the left here, we've got what could be called a classic electrolysis cell. You've got two electrodes, an anode and a cathode. They're immersed in a liquid electrolyte, an aqueous electrolyte. And you put an electric current through them. And when you do that, the one electrode produces bubbles of hydrogen, that's the cathode. And the other electrode produces the bubbles of oxygen, that's the anode. And then a very critical piece of part of the component here is what's called a separator, which is the thing between the two half cells. And the separator has very special properties. It has to allow ions, IONS, to flow between the anode and cathode to complete the reaction, but it has to stop the bubbles of oxygen from mixing with the bubbles of hydrogen. And the reason for that is that if you get more than around 4% hydrogen in your oxygen or 4% oxygen in your hydrogen, then that gas is an explosive mixture. You know, hydrogen and oxygen is rocket fuel, and so you don't want them mixing at all. And so that's what the separator does. Now, as I say, this is a classic cell. This was used for hundreds of years. Back in about the 1960s, people realized that you can actually reduce if you move the electrodes tight up against that separator, what they call a zero-gap electrolysis cell architecture, then you decrease the resistance, the electrical resistance between the cell, and you can use the electricity more efficiently. And then in around the early 2000s, people started developed what's called the asymmetric PEM electrolysis cell. PEM stands for polymer electrolyte membrane. It's basically a Nafion separator. If you leave one of the chambers empty of liquid, so it's not flooded, then you can have a direct production of gas in that chamber, and that also decreased the resistance. And so my students and I were thinking, well, what's the obvious next thing that's going to happen, right? And, let me maybe let me go back here then. How do I go backwards? Sorry about that. Well, actually, let me go here. And so we came up with this concept of what we call the capillary-fed electrolysis cell, where you have both chambers left empty, so not flooded, but at the bottom of the cell you have a reservoir which contains your water and also an electrolyte. And the point was that when you leave both chambers empty, you still need some way to supply water to the electrodes. And so the way we did it was to have a reservoir at the bottom, and then we had a separator which used a capillary effect to draw liquid up and supply it to the electrodes in real time, and it did that all the time. Okay, now I sort of jumped a bit ahead of myself here, so let me just go back a little bit to where I was there. So that was the challenge we were looking at. Now, at that time, we looked at, so this is a key feature of electrolysis cells, what's called a polarization curve. So every electrolysis cell has its own polarization curve, and it plots the cell voltage on the y-axis versus the current density on the x-axis. But these are effectively proxies. So the voltage is effectively a proxy for energy consumption. The higher the voltage, the more energy is consumed. And the current density is effectively a proxy for the hydrogen output. The higher the current density, the more hydrogen you produce. And what you see with all of these cells, and these are a whole series of academic and commercial cells published over the years, is that these curves all start at a point around here above 1.45 volts, what we call the onset potential. They all start there above at around 80 degrees Celsius. And if you're trying to make them more efficient, if you're trying to make these cells more efficient, you have to find a way to bring that cell down, bring that curve down. And so you have to then find a way to reduce what's called, reduce the onset potential. And we've spent a lot of time working on how to reduce that onset potential. It's not something that has been widely studied. But right at the present day, if you look at the best state-of-the-art commercial electrolysis cells, they consume around 47.5 kilowatt hours per kilogram of hydrogen produced. And that is, as I say, the state of the art. So the balance of plant, this gives you an idea of the conventional balance of plant. And what we've got here is just a schematic showing a series of cells in a stack, which are put together back to back. You pass an electric current through them, via these two terminals on the end, and all of the plus electrodes produce oxygen, all of the minus electrodes produce hydrogen, and you then have a separator between them. And what the balance of plant does in a conventional system, it has two pumps and it has two separate plumbing systems. So the left pump here pumps liquid through all of the oxygen-containing half cells and sweeps the bubbles off the electrodes to what's called oxygen separator tank. And in that tank, the bubbles and the liquid separate out. The bubbles form a bulk gas at the top here, which goes out at the top through a thing called a scrubber, and the scrubber removes particulates in the gas to purify the gas. And then you have another pump on the other side, and it's pumping liquid through all the hydrogen half cells. That liquid and bubbles, it's kind of like a froth or a foam, goes into the hydrogen separator where it separates out, and then you then have hydrogen coming out the top, going through its scrubber. And these are not normal pumps, they're not your swimming pool pump. These are very special pumps, hydrogen-rated or oxygen-rated pumps, and they're pumping typically large volumes of liquid through the system all of the time. If you don't do that, then the bubbles stick to your electrodes and the reaction more or less stops. So now also these systems produce a lot of heat because they're not very efficient, and so you need typically a water-cooled chiller to cool down the system, keep it at temperature, and you can have that on each return line or you can have it just on one. And then to replenish the water that's being consumed, you typically would have a pump up here pumping water into the scrubbers where it drips down and it replenishes the liquid that's being used. So what you can see is at least two large liquid circulating pumps, two gas liquid separators, a whole lot of piping, water-cooled chiller, and then you've got, in a typical alkaline system, around 10,000 litres of water per megawatt circulating all the time. So quite energy intensive. A typical balancer plant would consume between 2.5 to 5.5 kilowatt hours per kilogram. And the way you get to the 2.5 is just having a very large system so you can get economies of scale. But a smallish system, a megawatt, for example, which is still pretty big, would be using around 5.5 kilowatt hours per kilogram. And so the total energy consumed by a conventional system is around 50 to 53 kilowatt hours per kilogram to produce a kilogram of hydrogen. And hydrogen, as we said, contains, at best 39.4 kilowatt hours per kilogram. So there's a big gap between the amount of energy it contains and the amount of energy used to make it. And so that is what makes green hydrogen expensive at the moment. So so this was the cell then that we were trying to make, the capillary-fed cell. As I said, it has a separator that uses a capillary effect to draw liquid up and supply it to the electrodes. So the first thing we needed was a separator whose flow rate was enough to supply water so that the system didn't starve, that it could run indefinitely. And then the second thing we wanted to do was to come up with electrodes which could create bubble-free gas generation. In other words, what we wanted was the water here to be converted directly to the gas without going through bubbles. And the reason for that is because to make bubbles consumes a lot of electricity, a lot of energy. You can maybe remember when you were a kid in McDonald's trying to blow bubbles into your shake, right? And your cheeks got sore. It takes actually quite a lot of energy to make bubbles. So in this particular case, what we were trying was a new way of making bubbles, making the system bubble-free. And so what we were trying to do was to design electrodes which would draw liquid out of the separator, but just enough liquid to wet the electrodes and to wet them with a thin layer of liquid. And why it needed to be a thin layer of liquid was that when the gas was produced, we wanted it to dissolve in that layer, migrate through that layer and leave. If the layer is too thick, then the gas can't get away, and that layer gets supersaturated with gas, and you end up forming bubbles and wasting a lot of energy. And we were actually able to do that in the end, although it took quite a lot of work to figure out exactly how to tune those electrodes. So the first challenge was just to find a separator that would wick very rapidly, and we essentially searched through catalogues of filter membranes, amongst others, and we came across this filter membrane called a polyether sulfone microfiltration membrane, which we bought out of a catalogue, had an 8-micron pore size. We also had to design an experiment to actually measure the wicking rate, and I don't really have time to tell you about that, but it is described in our paper down here. But this is showing basically data from that experiment. So the dots, the solid dots, are showing the measured rate of capillary flow, and the lines are showing modelled rates. And you can see we developed a model which gave quite good match to the experimental data. So if we're wanting to sustain a current of 1 amp per square centimetre, we needed a flow rate of at least that, and 0.5 amp per square centimetre, we needed a flow rate of that. And you can see that at 80 degrees, which we couldn't actually measure but we could model, we could sustain an amp per square centimetre to a height of about 18 centimetres. It's about that high. So that's kind of about the height you need to make a commercial cell. And so we then set about testing this particular membrane as a separator to see how it worked. And we built a little cell. Actually, we built multiple prototypes. This was probably prototype number 5 or so. We used standard catalysts. We didn't use anything unusual. This is a standard industry catalyst, platinum on carbon, on a carbon paper. This is basically bought. We did synthesize a catalyst for the anode, but it was, again, a standard one, nickel iron oxyhydroxide. And then we welded what's called a bipolar plate to the electrodes and assembled the cell. We used an electrolyte of 27 weight % potassium hydroxide with this separator, and we were able to observe bubble-free water electrolysis, which was very exciting. And I will, if there's time later, I can explain to you how we knew for sure it was bubble-free. But this was really the key finding out of that work. So what we've plotted here is a polarization curve of our cell. It was a small cell, 1 square centimetre electrodes. But you can see, and we've compared it to the best polarization curves we could find for commercial alkaline and commercial PEM cells. And you can see it's substantially below that, meaning it uses far less energy to produce more hydrogen. And the main reason for that was that we had moved the onset potential down. You can see that the slope of this curve, which is actually a measure of the resistance of the cell, is almost the same as the slope of that. So these two cells have almost the same resistance. The difference is that we've moved the onset potential down, and that is what's created the improvement in efficiency. And that was because it had no bubbles. That was one of the reasons. There were actually several reasons. So the result of that was, at a typical current density of 0.5 amp per square centimetre, which is used in commercial alkaline cells, we were able to get 98% energy efficiency, corresponding to 40.4 kilowatt hours per kilogram for the cell. And that is actually better than the efficiency target for the year 2050 that was set by the International Renewable Energy Agency, IRENA, for electrolysis cells. And that was achieved in 2020, which is 30 years in advance of 2050. And you can see 40.4 kilowatt hours per kilogram cell consumption The best commercial cells today are 47.5 kilowatt hours, so a significant improvement there. Also for the balance of plant, just because the gases were produced directly in the cell, it resulted in a whole lot of simplifications in the balance of plant, sort of flowed on from that. So here's a cartoon showing a comparable balance of plant to what we had before. So there are 5 cells stacked here in series. Again, if you pass your current through the whole stack, they produce hydrogen and oxygen. The positive electrodes produce oxygen, the negative electrodes produce hydrogen. The difference is that you produce the gas directly in the cell. It's a bulk gas. It's not a mixture with water that has to be pumped somewhere else and then allowed to fractionate out, separate out. So you're not having that constant pumping of liquid through the cells. In fact, all you've got is a reservoir at the bottom, which you have to maintain the level of. And you can do that quite simply just by pumping in water, deionized water, to maintain that level. And so far simpler balance of plant. Because of the very high efficiency, 98% efficiency, is only 2% energy wasted as heat. And so you have far less cooling per kilogram of hydrogen produced per hour. And this is just comparing the capillary fed cell needs about 0.3 kilowatts of cooling, whereas per kilogram per hour, whereas commercial alkaline and PEM need much more, 7.2 kilowatts. So you don't need to cool it very much. And so you have a single small pump for your liquid. You have around 400 litres of water per megawatt, not 10,000 litres. You don't need gas liquid separators, you don't need all the pipes for that, and you don't need a chiller. You can do air cooling of the system. And so this balance of plant only requires around 1.01 kilowatt hours per kilogram. When you add that to the 40.4 kilowatt hours we had earlier for the cell, the total energy consumption is 41.5 kilowatt hours per kilogram, which is significantly better than the best commercial system out there. And in fact, the IRENA also has a target for the system efficiency of electrolyzers for the year 2050. It was that they needed to be less than 45 kilowatt hours to produce a kilogram of hydrogen. You can see we're already substantially below that. Today, the very best commercial electrolyzers require system energy consumption of around 50 to 53 kilowatt hours. So around a 20% improvement in efficiency. And that obviously has a big effect on the cost of the green hydrogen that you produce. And so once we realized all of this, we set up a spin-off company we called Hysata. That was spun out in 2021. And this is just a quick summary of the value proposition. So first of all, it offers the lowest levelized cost of green hydrogen in the industry, and that's mainly because we have much lower OPEX. It turns out we have a lower CAPEX because we have a much simpler stack and a lower cost balance of plant. It also turns out that this architecture is very amenable to integration with renewables. One of the issues with renewable energy is that it fluctuates. You know, as a cloud goes in front of the sun, your current goes down. As the wind stops blowing, and so you tend to have fluctuating currents with renewable energy. And a key issue for electrolyzers is to be able to follow that current. And so you need dynamic performance. Now, a lot of alkaline electrolyzers in general can't follow that sort of renewable energy very well because they have all this stuff pumping around all the time. In our case, we have very fast dynamic performance. In fact, we believe it's the fastest in the industry. It tracks changes in current extremely rapidly. We haven't been able to measure how fast it adjusts, but as fast as we can change it, it follows it. And so we can track renewable electricity down to almost zero, as it goes up and down. And then also, we specifically chose alkaline to make our system alkaline. We could have made it acid, but we specifically chose it to be alkaline because this is the most mature and robust technology. This is the technology that's been around for 200 years. And you can use low-cost materials, so you can use nickel catalysts, you can use nickel materials, whereas in acid-based systems like PEM electrolysis, you need to use titanium metal, you need to use precious metal catalysts, platinum and iridium, can avoid all of that stuff. And then right from the start, once we realized that we had something quite unique, we decided also to design the system for mass manufacturability. So electrolyzers have been around for 200 years, but they've been kind of a cottage industry. And so people have sort of built them by hand and kind of clunky manufacturing techniques. No one has ever built these things for high volume automated manufacturing. So we spent a lot of time working on that. In fact, before our first investors would invest, they sent 2 engineers to work with us to make sure that this technology could be turned into a high volume manufacturing process. And we actually worked with them for about 6 months before they would invest. But they were convinced at the end, and we have developed this now into a technique, into a cell that can be mass manufactured. So this is a cartoon, a very high level cartoon to show you what our cells look like. They're effectively made in the form, this is the Hysata cells, made in the form of a disc. We have an injection molded plastic frame that we attach our separator to. That's kind of welded to that. And then we have a cathode that fits in on the one side, an anode on the other side, and we have a reservoir at the bottom. And then we seal this with a nickel disc effectively on the outside on each side. So the whole cell is sealed. But it does have, and I'll explain to you how the gases get out and the liquid gets in a minute. And then we take these cells and we stack them inside a pressure vessel, and we're using just a stainless steel pipe, which is the cheapest pressure vessel you can get. You group them together, you put them into the pipe, and then you can make your hydrogen and oxygen. So I can't show you the exact design because unfortunately that is proprietary, but this will give you a high-level view of how we manufacture these things. So as I say, we injection mold a cell body, which looks like that, and you'll see it has these holes in it, which are called headers. We attach a separator to that. We can weld it in. Nowadays we weld it, but earlier we had a frame that held in place. We then have 2 electrodes, which are tied up against each side. We have a metal spring, a conductive spring, which goes on each side and provides the clamping force to hold the electrodes tied up against the separator. And then we have, as I said, this disc, which is they call it a bipolar plate. These are nickel discs on each side. They get welded to the cell to make a closed cell. And then you stack these things together, shown over here. And these holes, the headers, all line up, and they form what are called these like little tunnels inside the stack, and they connected downwards to each side of the separator. So your hydrogen all comes up, and goes out via one of these tubes. The oxygen goes out via another tube. And then we have tubes that carry water in and maintain the reservoir, and a tube that carries water out. And we've developed these now at full commercial size, and significant significant cells in stack, and they work, much as the original technology did. So developing these things, there are a few important factors we had to take into account. First of all was material selection. We had to develop sealing methods. We also had to design them for rapid movement on a production line, and so we wanted to keep the parts light. The main reason for putting these things inside pressure vessels is that the pressure inside the cell and outside the cell, between the cell and the pressure vessel, is much the same. And so the cell frame doesn't have a big pressure differential over it, and so it doesn't need to be very strong and robust. It can still produce gases at high pressure, but without being, big and heavy. And that was because we wanted rapid movement on the production line. And we also had to develop the stack size. So some of the lessons learned there was, first of all, there's a big difference between science and engineering. And I think, well, I've known this for a long time, but I guess maybe other people haven't realized it. You really should partner with engineers early. I'm a big fan of engineers. Some of the important lessons, we considered the need for high volume manufacturing from the outset. We developed the balancer plant in parallel. On previous occasions, we've tried to develop commercial cells. We've tried to develop the cell first and then the balancer plant, and that doesn't work. You need to do everything in parallel and make sure that that both work and they interact well. Supply chain is really, really important. You need to have your supply chains in place early, especially nowadays with COVID and supply disruptions, long lead times. You need seasoned design, process and manufacturing engineers, and we've been very fortunate in Hysata to hire some very seasoned and very knowledgeable design engineers and process and manufacturing engineers. So the value proposition, I'll just go back to the comparison of the capillary fed cell with the conventional cell. So the total system energy consumption 41.5 kilowatt hours per kilogram on the capillary fed cell, 50 to 53 kilowatt hours for a conventional system. So that's around 95% energy efficient all in, taking everything into consideration, versus around 75% energy efficiency all in for a conventional system. That has an enormous effect on the cost of the hydrogen that you produce. So what we've got here is an example, just an illustrative example of a renewable energy project producing 1 million tonnes of hydrogen per annum. And this is looking at it in US dollars. So there are innumerable energy export projects planned for Australia, and this is the sort of thing that they are looking at. So if you used incumbent electrolyzer technology, you would need 75% efficiency, 52.5 kilowatt hours. You'd need 14 gigawatts of renewables and around 7.6 gigawatts of electrolyzers to make your 1 million tonnes per annum. If you use the capillary cell system, 95% system efficiency, 41.5 kilowatt hours per kilogram, you only need 11 gigawatts and 6 gigawatts of electrolyzers. You still make your 1 million tonnes of hydrogen per annum. And if you look just at the renewables, there's a 3 gigawatt reduction in renewables. Renewables cost about $1 billion US per gigawatt. So that's a saving of $3 billion US right from the start. And the sort of customers that we are talking to at Hysata are telling us this is really a game changer for them. For many of them, it's the difference between being economic and uneconomic. So we've had a lot of commercial interest in this. And in fact, I think it's fair to say there's been truly incredible demand. Hysata has already signed up $5 billion in orders. Now, these are conditional orders, conditional on achieving the efficiencies that are shown there. But nevertheless, that's quite incredible, really, I think. And about 4 times that under negotiation. So there's really an opportunity here, I think, for us to hopefully make a big dent in decarbonising our systems, and also giving Australia a competitive advantage in energy export of hydrogen. So it's very exciting. I guess time will tell how it all pans out in the end, but so far so good. So let me end there, and I'll just acknowledge my colleagues down the bottom here who did the work, especially the first 2 colleagues here, Aaron Hodges and Lin Huang. They were the 2 PhD students who worked on this project, both mature age, and I have to say, excellent PhD students. They are now both working at Hysata, so they've actually created jobs for themselves which is great as well. And then I'd like to acknowledge also the organisations here that provided grants and funding. And thank you for your attention, and I'll be happy to answer any questions you may have. Thanks.
So no doubt plenty of questions. Hands up and we'll get into it. If you're a little bit tentative, I've got plenty I can start with, but no, yeah, Kevin.
Yeah, so very nice talk. My question is regarding the design of the electrolyzer. So if it's depending on the capillary, will there be a limit of the height that force can lift the liquid up, right?
Yes, yes, so that...
To me, it is much smaller than the commercial ones that go like 1.5, 2 meters diameter in the plate. Number two is you are sacrificing one side of the of your electrode. It's metal. Like one side is with water, the other side is in empty space.
No, I think they're both in empty space, if I can put it that way.
This will mean for one electrode, you have one side wetted, the other side is...
Yes, that's right, one side, but the electrodes are designed so the whole electrode gets wetted, both sides.
Yes.
But the gas tends to leave, as long as it can get through that thin layer. We think that's what's happening. The gas, so what happens with electrodes, as the gas is produced, it's dissolved in the liquid that's on the electrode.
The liquid spreads, wet the surface, right?
Sorry?
Liquid, wet the surface of
The surface is wetted, and the gas dissolves in that wet layer, and then it migrates away from the electrode. And if that layer is thin enough, then it can migrate and leave. The gases tend to migrate very slowly in potassium hydroxide. Actually, the migration rates are very well known. And we've actually published papers on quantifying those. So we know exactly how thick it should be. And as long as it's thin enough, the gas can migrate through and leave. If it's too thick, what we call overhydrated, then you end up supersaturating the liquid. And if you supersaturate it enough, then it will start forming bubbles, and then you don't have any efficiency benefit. So what was the other question?
The first one is about the height of capillary.
Yeah, so those calculations I showed you, 18 to 20 centimeters, that is if it's fed from the bottom. You can obviously also feed it from the top and use gravity, and that does lift that. But yeah, so the original work we did was all, looking at it from the bottom.
Yeah.
And so,
Fair enough.
yeah,
Thank you.
no worries.
But 6 inch or 8 inch steel pipe is a pretty cheap vessel, as you said. So there's some other things to think about.
Yeah, it's the cheapest. It's the cheapest pressure, and I think if you there is a trend in the industry to go to really big cells and stacks, and there are reasons for that. But the negatives of that is everything is big and heavy, and when you're trying to do high volume manufacturing, then big and heavy can only be moved slowly, whereas if it's small and light, you can move things fast, you can manufacture at speed. And so there are many different things to consider in these scenarios.
Yes.
Hi, Quentin from RMIT. Coming back to when you were showing the different efficiencies for the different current densities that you achieve, and you highlighted the one where there was one at 100%, which is quite impressive. And so what you said is basically it's a kind of a twofold question. So what you said is basically the difference is cutting the work that you need to generate the powers, and that's also working on the initial threshold in voltage that you have. But so why the choice of putting yourself at that sort of current density when you don't get the best efficiency? Is there a particular reason?
To not operate at 100%, is that what you mean? Yeah, so look, it's a fine line. So 80% of the cost is the cost of the electricity. The other 20% is the cost of the capital equipment. And there is a balance there. There's a sweet spot there. And so if you work at 100% efficiency, yeah, you'd get very good OPEX, but your output of hydrogen is less. And that increases the CapEx cost. And so you kind of have to find the sweet spot there. The sweet spot is typically, we think, is typically around 98% efficiency in our case, 500 milliamps a square centimetre. So, and we have techno-economic modelers and analysts, or Hysata has analysed that, and that is their conclusion is.
So even with the cheap material that you're using, it's still not that cheap when it comes to actually starting, right?
Well, it's not so much the materials of the cell, they are cheap, but the balance of plant. You have to have, gas sensors and all sorts of stuff, PLCs and that stuff, it all adds costs. So.
Yep.
What's the patent situation?
Yeah, so we have got a number of patents on these. We've got full patents on the technology itself, and then we've got another 6 patents around that. Other parts.
Which countries around the world?
Yeah, worldwide, yeah.
Carefully done. Carefully done.
Helena from chemical engineering. So very interesting talk. My question is, what happens with water and electrolyte flow out from the cell and the step inside, and when the electrolyte become concentrated?
Yeah, so that's a very good question. Now, let me just summarise, for maybe not everyone heard it. So, I guess the capillary effect, maybe let me go back to that picture. Oops. Hope I didn't do anything there. Let me just find that picture. Yeah, so I think the question that's being asked is, you've obviously filled the separator with this liquid electrolyte, and so initially when you start, it's all the same molarity of the KOH in there, but once it starts operating, you are converting water in the separator to hydrogen and oxygen, and so the concentration of KOH in there should just keep increasing, right? And so that was a key concern for us early on. What we found was actually quite remarkable. When you run this thing, yes, the concentration should increase, but it doesn't. And what happens is water goes up and replaces the water that's consumed totally spontaneously, and the KOH concentration remains the same everywhere in this thing all the time. Doesn't matter how you run it, hard, soft, doesn't matter what. And so we think that there's a capillary effect drawing the water up, but there are other effects going on there as well, we think, and one is maybe an osmotic effect. So osmosis is the process where water will move from an area of low concentration to an area of high concentration to equalize it, and we think that could be a driving force here as well. But as long as you have the liquid in the system is mobile enough, it keeps the whole system at the same concentration all the time. So all that we do is add replenishment water to the reservoir. We don't have to add it anywhere else.
So there's a gradient of KOH up it, which is itself in equilibrium.
Well, there's no gradient. It's the same everywhere, all the time, that we can measure. We've looked for that. We were concerned that there may be a gradient, there may be more KOH at the top than the bottom, and we've studied that in depth, but in this system it's the same everywhere all the time, and it just spontaneously readjusts.
Any questions?
Hi Jerry, Aubrey from Temasek, thanks.
Hi.
for the chat.
Yeah, hi.
Again. I'm curious and hearing a little bit about your experience of spinning out Hysata, bringing the PhD students with you out of UOW, and I think you've set a great example and story for Australia. And the context behind my question is, I think it's arguable that if we think about sort of commercialization and spin out of climate technologies, the US kind of sets the bar and the Boston ecosystem, Stanford ecosystem. So, how do we get the Australian ecosystem moving more in that direction? What are the challenges there?
Well, let me say firstly, I've been working in the Australian ecosystem for many, many years, and it is improving in leaps and bounds. If I look at our last capital raising, or the initial capital raising we did here, it was so different to capital raisings I did, even 10 years ago. Just astonishingly different. So I think things are changing in Australia very rapidly and very positively, I think, in that regard. In many ways, and I think it's not just Australia, Silicon Valley kind of set the model, and the rest of the world is slowly catching on and replicating the things going on there. So in terms of commercialisation, so I have a very unusual position at Wollongong University. I was actually appointed to commercialise stuff, and in fact, I originally went back to Wollongong University in 2010 with a job to commercialise the technology, which we did at that time. And at that time, I think I was absolutely totally unique in Australia, probably in Australia, but definitely in the University of Wollongong to do that. Now I think that is more common, and I think people are looking at that sort of model much more. I think there's a lot of scope, for people dedicated to do that, academics who are interested, and maybe I'm a little unusual also as an academic in that I just enjoy the thrill of, other people paying for something you do. It's kind of a vote of confidence rather than, publishing another paper. And I know maybe I'm unusual in that respect, but I find that quite thrilling. So that sort of is what floats my boat. But I think there's scope for that. And I think, and in terms of the actual process of commercialisation, when you are an academic, every academic learns how to apply for grants. And there's a formula, and there are people who help you, and you follow the formula, and if you follow it well and you've got a good story, you get a grant. And I think commercialisation is much the same thing, except it's a different formula. And it's a different way of doing things. And that's all just education as well. People, if you learn how to do it, and you learn then what is a good idea, just like with a grant, you learn what is likely to get a grant and not. You can see with commercialisation as well. So it's education, I think, and changing the mindset also. So, but I have to say, I think Australia's actually making great leaps and bounds.
A good friend of mine who's commercialised a lot of inventions says the definition of an inventor is someone who sold an idea, not had an idea. Sold an idea. Much harder thing than everyone. Yes, sir.
How long do you expect an individual unit to last? Is there anything that degrades it?
Yes, so typical conventional systems, the cell stack will typically, for alkaline, will typically last about 10 years. So 90,000 hours is a typical benchmark. And the thing that usually degrades it, there are actually many things that will degrade performance, but usually it is the catalysts on the electrodes slowly degrade. So after 10 years, you typically swap out the cell, the whole stack, and carry on. The rest of the stuff, the balancer plant, will typically last 25 years plus. So, and I think in our system, we've got a very good chance actually of lasting more than 10 years, because one of the reasons that the catalysts degrade is the bubbles. Bubbles tend to have, there's a lot of mechanical forces there which can degrade the surface of your electrode. Without bubbles, we expect that we should have longer lifetimes, but we still have to test that and run that.
And I've got a bit of time, I think, a couple more minutes. Aaron.
Very good talk. Just wondering whether you see any problem with the QH, for example, not along the cell, but across the cell. For example, do you see QH salts or something?
No, that was another thing we looked at very carefully. If there would be any dry spots or anything like that, and there are situations where you can get dry spots. That is obviously very bad. because if you get a dry spot, then potentially your gases can go through that and mix. So, but we've done a lot of work on that, and yeah, you actually got to try quite hard to get dry spots. If you design it right, then you don't have any trouble with that.
One more question from the back.
I was wondering what your target price of output is.
Our target price?
For the output, target price for the output.
Yeah, so we're targeting less than $2 Australian a kilogram. And we're hoping to get that. That does depend on a number of things. It depends on the cost of renewables coming down as it is doing. But we're hoping to get that by 2030. And hopefully, it depends on many things, obviously. But if we can get that, that would be near the tipping point where it will become competitive, economically competitive with fossil fuels. And I think once you reach that tipping point, then this whole industry will go on its own. It doesn't need any subsidies or anything. It will be profitable and it will run on its own. And I think that's where we have to try to get it. That's exactly why I think the Australian government targeted $2 a kilogram. And just to give you an idea, a kilogram of hydrogen contains about as much energy as a gallon, or American gallon of petrol, so about 4 litres, 3.8 litres.
That was actually Angus Taylor's target for hydrogen, $2, but that's about $16, $17 a gigajoule, which is about less than half the wholesale cost of petrol today. So unsubsidised, but no subsidies. Petrol is more than $30 a gigajoule today. So to your point, this is why I've always wondered.
Yeah, but I think you were the one telling me that internal combustion engines are, 36% efficient?
Yeah.
Whereas a fuel cell or something...
I'm saying it's the cost of the energy,
or
whatever it goes into. So if you're producing a fuel which is cheaper than gasoline and diesel without subsidy, then to your point, then it's game on.
Yeah, exactly.
And that's I think, remarkable. And just closing out, Jerry's device, the efficiency is so much higher than the others. It's almost, the cost of hydrogen is almost proportional to inversely proportional to your device efficiency. So if you go from, I think 75 is pretty generous for the state of the art at the moment, but 60-70% efficiency up to high 90s, you're talking about a 30-40% reduction in the cost of the hydrogen. And that dramatically change things. Now, I was going to close it out then. We're bang on 6:30. Maybe there's a little bit of time for a few questions one-on-one at the end. But please thank Jerry for coming along.